Okay, so this is the fourth of four big proof explanation type problems that we're going to be doing this year. Um, so the the main gist of it is, so far you've figured out how to write tangent planes if I give you a function that's explicitly defined. So z equals some function of x and y, and I give that to you in terms of x's and y's only. So like x squared y plus 3x squared plus 7. If I said, come up with the tangent plane at the point um, 1, 2, you could do it because in proof number 1 that we did for this chunk of 4 proofs, we learned that you could write the tangent plane as z minus z naught equals, and z naught would be f at 1, 2. And then you've got your f sub x at the point 1, 2. And then you multiply by x minus x naught, which is x minus 1. And then plus the slope in the y direction at 1, 2. And then you multiply that by y minus 2, right? Y minus y naught. Well, that's great if you have a function z equals all the other stuff. But what happens if you have a function like, let's say, 3x squared z squared plus 2yz plus sine z, zy even, let's make it worse, equals 4. Well, that's implicitly defined. It's not easy to get z by itself. It might not even be possible, I'm not sure, to get z by itself there. So what we need, but that's still a surface, and it still has tangent planes all over the place. So what we need to do is be able to come up with a way to come up with the tangent plane equation for functions that look like this. So that's what this general idea does here. That's what we're going to derive here. So keeping that in mind, let me erase this stuff. And let's look at our surface here, and we'll define some things first. So let CB be any curve on S, on our surface S, through point P. P is where we're going to get the tangent plane, by the way. This means that we can define, since C is a curve in 3 space, we can define I'm sorry this is taking so long. We can define C by a continuous vector function. Vector function R of t. And I'll write it like this. It'll be the x component with the t, y of t, and z of t. Okay. And then p, so p would be specific to some particular t value corresponding to this vector function. So let t naught, or let's say let t equals t naught be the parameter value corresponding. Oh my gosh, this pen is just brutal right now. Nothing erases. There we go. Hold on, let me pause and see. All right, sorry, I just paused for a second, just hoping that I can fix this marker. Okay, so let t equal t naught be the parameter value corresponding to point P. Nope, didn't fix it. The point P. So R t naught equals x naught, y naught, z naught. And the point P in the original part of the problem is defined as x naught, y naught, z naught. Okay, so at t equals t0, we've got this vector right there, whose endpoint is x naught, y naught, z naught, which is P. Okay, let's see, what's next? So since C lies on S, we can say any point or any, let's say, point x of t, y of t, z of t, must work when substituted into the equation for S. Right? Any point on C has to also be on S. And we know that all the points on C follow the form x of t, y of t, z of t for specific t values. And if I plug that into S, it should also work. Well, S is defined by some big function in terms of x, y, and z equals some constant value k. Okay, kind of like the example that I wrote earlier. So I'll put a semicolon here. That is if I plug them into F, so if I plug x of t, y of t, and z of t into F, then I should get that k back, that constant. Okay, so that's kind of the groundwork for this. So now we're going to use the chain rule. Okay, so I'm going to take ddt of both sides. ddt of capital F of x of t, y of t, z of t. And on the other side, I'm going to do ddt of the k. Well, okay, so we got to use the chain rule here. So we get df, whoops. So we get df dx times dx dt plus df dy dy dt plus df dz, that's a curvy d, dz dt. And then on the other side, derivative of a constant, 0. Okay. So let me rearrange this a little bit. This I can write as, I'll use some slightly different notation. Capital F sub x times x prime of t plus capital F sub y times y prime of t plus capital F sub z add z prime of t equals 0. Well, okay. I can write that as a dot product, where the first part is f sub x, f sub y, f sub z, and the second one is x prime, y prime, z prime. Okay, well, if you think about this, r of t is x of t, x of t, y of t, z of t. So this right here would have to be r prime of t, right? Because you just take the derivative of each chunk. So I'm going to rewrite this as, oh, and this thing right here is going to be the gradient of f. So this is gradient of f, let me say therefore, the gradient of f dot r prime of t has to equal 0. Okay. So here, we're going to kind of use that. In particular, that says particular. When t equals t naught, we have, oh my gosh, that the gradient of f at x naught, y naught, t naught, z naught, sorry, dot r prime at t naught has to be 0. Okay, well, since the dot product is 0, and since the gradient of f at that point does not equal the 0 vector, which it's kind of buried up here. It's an assumption that we're making here. And we'll talk about what happens if it is 0 at the end. And r prime at t naught, oops, sorry, this has a naught up here. I forgot it. I think I said it but didn't write it. Does not equal the 0 vector, which, by the way, I'll come back to this, so let me star it. We know that, let's see, what can we say? We know the gradient of f is going to be perpendicular to r prime of t. Which is the tangent vector. tangent vector to C on S at P. Now remember, C can be any curve that passes through P that's on point S. So C doesn't have to be this purple one. It could be something that goes through like this or something that goes through like that. And it turns out R prime of T is a tangent vector. So R prime of T, depending on what your C looks like, could be any number of vectors stuck in the tangent plane. And what we just figured out was that the gradient of F has to be perpendicular to those, which means it's got to point right out of that plane right there. Right? It's got to be perpendicular to it, so we found a normal vector to our plane. Okay, so let's come back down here. So therefore, the tangent plane at P can be found by taking the dot product of gradient of F at x naught, y naught, z naught, and a general vector in the tangent plane T and setting it equal to 0. Okay, because the key is get a normal vector to your plane and then get a general vector in your plane and dot them and equal to 0, right? So based on this, therefore, T is defined by gradient of F at x naught, y naught, z naught, dot the general vector in the plane, x minus, now the point that we know is x naught, y naught, z naught, and equaling 0. Okay. So we could actually go a little bit further. We know that, so this is the main idea right here, getting the tangent plane now. Now we know gradient of F at that point is normal to the tangent plane at P. T at P. Okay, so that means that we could write the normal line equation. Therefore, the normal line to S, or to the tangent plane at P, is given by, hold on, and now what I'm going to write is something that looks like this. It's R of T equals some original vector plus a direction vector times t. You guys remember that? So here's how it works. It's going to be xyz, or if you wanted to call that some version like r of t or something like that, but we've used r for other stuff. Well, you need an initial point that it goes through, and the initial point that we know is p, which is x naught, y naught, z naught. And then what I have to add to it is a direction vector multiplied by various increments. Well, this is going to be, well, I need this bigger, sorry. There's the eraser. So the x component, f sub x at x naught, y naught, z naught, f sub y at x naught, y naught, z naught, and f sub z at x naught, y naught, z naught. This is driving me nuts. All right, times t. Don't forget the t over here. In fact, I'll put it right here. That's where we usually have been putting it. Okay, now let's go back up to that starred line here. We assume this, and I just stated this as though it was an assumption. So let's talk about this one that we first assumed. Okay, if the gradient was the zero vector, then it turns out that I'm not going to bother proving it, but it turns out you don't necessarily get a nice surface S. You get these weird random points all over in 3D. And it's often called an exotic collection of points in 3 space. Exotic, yeah, okay, great. The other thing is, if r prime of t was 0, so I'll put this down here. If r prime of t did equal the 0 vector, then r of t would be, if you integrated, you would end up with some constant vector, a, b, c. Well, if that happens, so that's a constant vector. This means, and remember, r was how we defined, r was how we defined c. C was r of t. Well, if r is a constant vector, then c is only a single point. So let me write that down. Then c is only the point A, B, C, little c. Okay, but C was defined as any curve through P. Well, if the only curve through P is this one, then the surface, so by this logic, this would mean that the surface S would only be point P, because if C is any curve through P, and any curve through P has to be written as a constant vector, then that's the only point on your entire surface. S is only one point. And if you only get one point, then there's no tangent plane there. You can't say what's tangent at a single point when there's only one point to look at. No tangent plane. So it doesn't make any sense to assume that r prime of t is 0, because otherwise you don't really have a surface to look at. You only have a single point. All right. That's it. I hope that helps. That's the last big thing for the unit. All right, take care.